about the atmospheric turbulence and how it relates to the wind energy field, which I mean it really goes along with the previous presentation because he talked about the airfoils and all of that, which is also a big part. And also, when doing this research, atmospheric turbulence isn't called turbulence most commonly. It's commonly referred to as wind wake because it takes a lot of the information from um, airplanes and all that. So, why is it important for us? Because over the most recent years, we are now looking for more renewable options. So right now I have a map. This was a couple years back from NREL of the United States as well as the state of West Virginia, showing the wind potential at that kind of the annual average speeds, both of them at 80 meters. And you can see on the West Virginia's, most of our wind potential is toward the eastern part of the state along the mountain ridge, which is very typical for wind energy. There are currently there's two main projects, and then we have the Mountaineer Wind Energy Center, which conducts research and does a lot of testing. But Beech Ridge Wind Farm has a 100 megawatt capacity and has 67 GE 1.5 megawatt turbines. And Mount Storm, which is towards the eastern part of the state and closest to Maryland, what is owned by the Shell Energy Company as well as Dominion Energy, is a 264 megawatt capacity with 132 2 megawatt turbines. So there's a lot of energy out there in a couple of projects, and West Virginia is really trying to incentivize companies coming to West Virginia because they're trying to open up the field of renewables. I'm not sure how much information you guys already know about wind turbines, but I just kind of put up this picture of a bunch of common ones. The one I'm going to be talking about is going to be the one on the left, the one that we're most common seeing. It's the horizontal axis wind turbine, and then the rest are vertical ones. And for you guys who don't know, here are the components of the horizontal axis wind turbine. And the main thing that we're going to focus on is the blade, because that's the one that's, most related to turbulence. But, the rotor, all that does come into play. So here is the blade design of the horizontal axis, which, like in the previous presentation, we talked about airplanes, and that's where a lot of this came from, which essentially propellers and older windmills. And this is just kind of a standard one. And you can see the side view of the blade, and you can kind of see the components and how it's has to be reinforced in those sort of blue part. If you can see my mouse, that this reinforcement goes from the bottom all the way towards the tip, as well as a couple other parts of reinforcement here because they are put under a lot of stress depending on the size and just the rating of the wind turbine. For this presentation, I was mostly talking about more larger ones that are up 80 meters, 80 meters high, more typical for larger scale energy production instead of small scale. And I have a couple videos later on that shows it. So now I have these two figures. One of them is just the wind power versus months for Washington, D.C., and the other is the wind speed measurements over a 1 minute interval for 10 minutes. And I know we've beaten this to death, but you used for turbulence, it's very common to use the Navier-Stokes equation, as well as having the turbulence is what depends on the capacity of wind turbine, talks about the Reynolds number. But for the larger scale ones, you're mainly focusing with a larger Reynolds number. And then in the previous presentation, how he said, the bird's only facing around 2,000. That would be more common for a individual turbine, more lower height. So that's maybe 10, 20 meters high. So it's a personal use one. before, like, when you start talking about like offshore wind and large scales like the Mount Storm project, you're going to be dealing with a lot higher Reynolds number because of the wind speeds that they're facing. And also, use statistics is also very prevalent in the wind energy field, because for like on the one on the left, for the wind power, they find the average, so they kind of know how to fund these projects to see if the money's going to be worth it or not. And they usually have to do these over a couple of years for investors to really back them, as well as having states that have a lot of friendly policies. And let me get into these videos I have to show you kind of the effects. So here I have the wind turbine start up with turbulent flow, and I sped it up, but you can, I'll go back. So here's it starting. As you can see, it's pretty uniform around, but as you can see, it's gonna speed up, and you can get to the side profile, and you can really see the mixing of the air as it's relating to the blades. And this is just for a single wind turbine. I have one, my next video is going to show you when it has multiple ones, like, because you never just have one turbine unless you have an individual one. You usually have multiple, sometimes next to each other, behind them. And I was able to find a couple of videos that kind of really shows, and see here's at it more towards its normal operating conditions. And this one is one that on the left you can't really see on the left, but on the right it has them in black. You can see the turbines that are behind each other, and there's two of them right here and here. And it's just a good video. Oops, sorry, turn down the volume. To just show how from behind you can see the disruption of the wind behind it. And this simulation was done by the National Research for Energy Labs. What was that? And my last short clip I have is two turbines operating in line with each other. This was done by APS Physics, and I thought it was just a really neat simulation that showed the velocity behind it. And so that first one was when the turbines were in line with each other, so one was behind the next. This one, they have a slight offset, which is more common in practice. And you can just see how different each of the streams are now, from comparing from that one to having it and one in front of the other. Makes it look almost like uniform, almost like the second one's like not even there, but you can see where it would be based on the change of the velocity from green to blue, like right here. And so going back to my presentation, there are a couple experimental examples I saw and reviewed. I wasn't able to get two of them from the West Virginia Library in time for this. They said I didn't cite them correctly for them to get, and that one of them wasn't in English. So I had to make do with the one I had. And the one that I had used a wind tunnel with a small scale wind turbine of the horizontal axis, with the common one. And I'm not sure if you guys are familiar with wind tunnels, but they usually have one opening to allow, kind of consistent flow. And this example that I have it cited later on, like in my presentation, they wanted to see the effects of turbulence versus power output on the small scale. So how they created like a more turbulent flow was they just put a mesh over the opening where the wind comes in. They had a fine mesh and a coarse mesh, and then they then they graphed the profiles and they did it two-dimensionally instead of three-dimensionally. And I'm gonna pull that up in a second. And it was really so. I'll start with this and stuff. So here's the results from the like the finer grid. As you can see, this is the power coefficient, and these are the heights of that they set it. And you can see there's a lot more grouping in the coarser one compared to the fine one. And let's see if here's one of the profiles. There's one that has a next, yeah, here. The downwind velocity distribution for the fine one on the left and the coarse one on the right. You can see the coarse one has a lesser angle than the fine one, which, I mean, they previously up, yeah. So here's the example when they had the wind tunnel, the fine, I think it's an 8 mm length versus a 40 mm. And then this was our experimental setup. And just after doing the reading and all these presentations, it's very important that they take turbulence into consideration, because a lot of damage occurs when the wind speeds get too high. That's why the wind turbines, let me go back, they have these yaw drives and yaw motors to one face them in to the wind to get the most wind power. But also they have most wind turbines have a cut in and cut off velocity. So when the rotors are going too fast, when the wind speed's getting too fast, the turbines will move out of the way of the wind. So it prevents damage to the motors, damage to the blades. And let me go back. The most damaged part, can you guys see my mouse? Right here. That is where most of the damage occurs on wind turbine blades at high speeds and even low speeds with certain turbulent conditions, because at the tip, there is so much force, because that's where the fastest speed occurs, at the tip, that it's kind of like a safety feature, because they don't want it breaking, because once wind turbines break their blades, there's no really, a lot of landfills won't take them because how big they are. So, and they're also very expensive to make as well as to transport and to put on. There's a lot that goes into it. So that's really taken into consideration. Do you guys have any questions? So I talk pretty fast, so sorry.
That's okay. Thank you very much. And please, questions from the audience first, please.
Yeah, I have a question. So can you point out the wind projects on the third slide on the map of West Virginia so I can see where, like, location, if you don't know specifically where they are?
Yeah. Fine. Well, one I drive by all the time, so I'm very familiar with that one. The one, hold on, let me move this. There is one that's like right around this area. So it's more towards like what, 7-ish meters per second average. And the other one, I believe, is somewhere out this way. I believe it's Mount Storm is the one that's the closest to Maryland in kind of this sweeter area. And I know the Beech Ridge one is also in the northern or northwestern part of the state, if I'm correct.
Okay. Do you think that we built those before we actually did this wind speed average thing? Because it seems like the one right at about 7.5 meters per second would be a lot more efficient than the other two that are at about 4.5 meters per second.
Yeah. A lot of the cut-on speeds for the larger ones, they won't even start moving till about they usually cut on around 2.5 meters per second, which is about like 6 miles per hour. But I know the one at Mount Storm is more closer to ideal range. But I know there's a lot of pushback with the, like, you know, just local government and state government that, you know, West Virginia really hasn't been a really renewable energy driven state. It's kind of starting to slowly get there because, you know, West Virginia is the king of coal, always known for its coal mining heritage. And if they start embracing, you know, like, oh, we're all going renewables, it's just like, but I mean, there is opportunity, but then again, you still have to do the land lease agreements. You have to figure out distribution. There's just a lot more that goes into it. I mean, like numerically speaking, yeah, like you could just put a bunch of the wind turbines on there and you get energy, but there's a lot more that goes into it, unfortunately.
All right, cool. Thank you.
Yep.
Thank you. More questions, please, from the audience?
Yeah, I have a question as well. Does it impact the efficiency of them, say when they're like front to back versus lined up side by side? Because I know a lot of times you'll see them, especially on the ridges in West Virginia, they're normally side by side. There's not any depth to the amount of them. Because, you know, when you have them front to back, you're going to have ones behind them running in the wakes of the ones ahead of them. So does that impact the efficiency of them?
It does slightly. I don't have any like definite numbers. I mean, I just remember doing this on my undergrad and doing research on my undergrad. But when you have all those wind turbines on those peaks, they turn into the wind. So they all would theoretically all be facing the same way if the wind's blowing the same way. But because of the spacing, they're sometimes back and forth because they want to be at the ridge line. But it only affects it. It's nothing too great. I know that. I know it does affect them, but not as much as it's not like solar panels. Like if you put one above another one, it blocks the shade completely, and you only get like nothing. Wind will still go around it, and as long as it's still at the right speed, it'll still push the turbine blades.
Okay, thanks.
Yep.
Okay, thank you very much. More questions, please, if any? Then let us thank our speaker again. And Catherine, you are the same, the next one, right?
Yes.
Yes, okay, let me just switch share screen. Okay, so let me just
Let me just
finish it and I will switch to you back.